Hello everybody, and welcome to the first video for Cumulative Review Packet number 9. We'll be going through numbers 1 through 10 with me, and then 11 through 20 with Mr. McConey. So, if I take a look at numbers 1 and 2, it says we want to write these both as a single trig function, and after we have a single trig function, we would like an exact answer, and that usually means we are going to use the unit circle to find that. So if I look at the first one, I notice it has cosine of 300 degrees times cosine of 15 minus sine of 300 sine of 15 multiplied. Whenever I see something that is subtracting, and like number 2, I see things that are adding and subtracting, my mind goes to either a sum or difference formula. So I need you at this point to find your Unit 5 packet that again looks like this. Precalc Unit 5, and it has the unit circle on here, it has all your identities, and we're going to focus here on the sum and difference formula. The one that we just had, if we look back, was cosine cosine minus sine sine, which if we look at the identities, cosine cosine minus sine sine, if I reduce that to a single trig function, is cosine of the first angle plus the second. So if I go, sorry about that, if I go back here, we could rewrite this as a single trig function like so. This is really the same as cosine of a plus b, which is the same as cosine of 300 degrees plus 15 degrees, because a would be 300 and b would be 15, which is cosine of 315 degrees. 315 degrees, if you look back at our reference sheet here, is on the unit circle right here, and we are looking for the cosine or the x value at 315 or 7 pi over 4. The x value is positive root 2 over 2. So if I take a look here, again, we're looking for the x value at 315 degrees, which would be root 2 over 2. Number 2 initially looks more complicated, but if we'd like to take this from a crazy situation to a single trig function, my eye again goes to a sum or difference formula because I have both sum and a difference. So if I look at my reference sheet again, I have a plus on the top and a minus on the bottom. So whenever I have a plus on the top and the minus on the bottom, that is really the same as tangent of a plus b. So, sorry that I keep doing that. So if I go here, this is the same as tangent of the first angle, 5 pi over 4, plus tangent of the second angle, which is pi over 12. And above that, I'll write a note that I'm using the identity tangent of a plus b. Now, in order to use the unit circle, we need this to be an angle that we recognize. So we need to add these two angles in radians with a common denominator. And to do that, I need to multiply this first fraction by 3 over 3. So I could get 15 pi over 12 plus pi over 12, which would be tangent of 16 pi over 12, which is the same thing as tangent of 4 pi over 3. 4 pi over 3 is on our unit circle. And remember, tangent really is y over x. So if I look at my unit circle and look at 4 pi over 3, which is right here, if I take the y value, negative root 3 over 2, and divide that by negative 1/2, let me write that here. So that is really negative root 3 over 2 divided by negative 1/2. You could show that work, or some of you might remember that if you do that, you might have memorized at this point that the tangent values at any 60-degree based angle is a form of root 3. Because it's in the third quadrant, it has to be a positive root 3. So my answer is positive root 3. Number 3, given that cosine of angle x is equal to negative 5/13 and sine of y is equal to negative 9 over 41, both angles are in x and y are in quadrant 3, so we have to probably draw some triangles here. We first want to find sine of x minus y. So the first thing I want to do is draw a picture. The triangle with reference angle x is given is that the cosine, or the adjacent over hypotenuse, so negative 5 over 13 is given here. This is a 5, 12, 13 triple, and the 12 has to be negative because it is in the third quadrant. The second situation is also in the third quadrant. This time our reference angle is y, not x. Sine is opposite over hypotenuse, so that would be negative 9 and 41. This, if you could do the Pythagorean theorem, or some of you might have memorized, this is a 9, 40, 41 triple. And the 40 also has to be negative because the x is negative in the third quadrant. Now that I have my two situations, you can use your reference sheet again and write that sine of x minus y is really the same. Again, I'm using this, sine of a minus b, or sine of x minus y, if you want to use this as a reference here. So I'm looking at this right here. That would be sine of x cosine of y minus sine of the other angle, y, cosine of the other angle, x. And we can use our triangles to replace the values that we know. And I'll start with the red triangle here. Sine of x, opposite over hypotenuse. Let me use the correct color. Sine of x is really negative 12 over 13. And cosine of x over here is really negative 5 over 13. From the second triangle, cosine of y is really equal to negative 40 over 41. And then we have a minus here in the middle. And we have sine of y equaling negative 9 over 41. If I multiply this out, negative times negative is going to be a positive. If I multiply 12 times 40, that gets me positive 480 over 13 times 41, which is a lovely denominator of 533, quite large. Then I have three negatives minus a negative and another negative. Negative times negative negative is still negative. 9 times 5 is 45. 41 times 13 is again 533. Now that they have same denominator, I can combine them, and my answer would be 435 over 533. And no, there is no greatest common factor you can take out of both. If I would like to look at part B and find cosine of 2x, I am only going to use this first triangle here, because I don't care about reference angle y, I only care about reference angle x. So if we use our reference sheet again and look at cosine of 2x, or a double angle identity, I'll write that here, double angle identity. If we look at our reference sheet, I can see that cosine of 2 theta, or cosine of 2x, is equal to any of these three right here. My favorite is cosine squared theta minus sine squared theta, but in this case we could say cosine squared x minus sine squared x. So if I go back here, I can replace this identity with cosine squared x minus sine squared x. The reason that's helpful is because this triangle has to do with x, not 2x. So if I rewrite the identity as so, I'm only dealing with a single rotation of x. And because I have the triangle, I already know what cosine is. As a reminder, what this really means is you're finding your cosine value and squaring it, then finding your sine value and squaring it, which we already know from here. The cosine value is negative 5 over 13 squared. The sine value is negative 12 over 13 squared. If I square a negative, it always becomes positive, and you square both top and bottom. So it would be 25 over 169 minus negative times negative is still a positive. This negative, if it's squared, becomes a positive, but this one stays. So that's 144 over 169. If I subtract from left to right, that would be negative 119 over the common denominator of 169. And just like the last example, there is no GCF I can take out of both numbers. Number 4, evaluate using a sum or difference formula. And again, feel free to use your sum and differences as a reference. But the first thing we'd like to do is figure out how we want to split up 375 degrees. And we want to do that by using values that are on the unit circle. The ones that I looked at, if I look at my unit circle as a reference point, is I said that 135 degrees plus 240 degrees is going to equal 375. So what we could do is rewrite this as the tangent of angles that we recognize. 135 degrees plus 240 degrees. And as soon as I write it as tangent of a sum, I can use this identity. Tangent of the first angle plus tangent of the second angle over 1 minus tangent of the first angle times tangent of the second angle. Or in this case, tangent of 135 degrees plus tangent of 240 degrees over 1 minus the tangent of 135 degrees times the tangent of 240 degrees. The tangent of 135 degrees, if I look back at my unit circle, 135 is right here. If I take y divided by x, that is going to be -1, my tangent value. So anytime I see tangent of 35, I'm going to replace that with -1. So we have -1 plus, we'll figure that out in a second, over 1 minus tangent of 135 is also -1. If I look back at my unit circle for the tangent of 240 degrees, 240, I think we already talked about earlier for a tangent value. It is a 60 base angle, so any 60 base angle, the tangent value is √3. Because it's in the third quadrant, it has to be a positive √3. So that means this is replaced with positive √3, and this multiplication is also replaced with √3. So if I clean this up a little bit, we have -1 plus √3 on the top, and on the bottom we have negative times negative, 1 plus √3 on the bottom. Now you may recall that we cannot have a radical in the denominator. So what we use here is the idea of the conjugate. We need to multiply top and bottom by the conjugate, or 1 minus √3, because when we multiply by the conjugate, 1 positive, 1 negative, the middle terms tend to cross out. So if I use FOIL or distributive property on the top, -1 times 1, I get -1, then I get plus √3, then I get plus another √3, and then I get minus technically √9, which is really -3. And in the denominator, again, when I multiply by a positive and a negative, the middle terms cross out. As you can see, you're going to get a negative √3 and a positive √3, so that's just going to cancel out anyway. So all we need to do is multiply 1 times 1 and multiply √3 times negative √3, which is again -3. If I keep simplifying this and combine like terms in the numerator, that would be -4 plus 2 √3s all over -2. And then you can think about dividing this term by -2 and this term by -2. -4 divided by -2 is a positive 2. 2 √3 divided by -2 is technically -1 √3, but the most simple answer is just 2 minus √3. And these are not like terms, so you leave them separate. Number 5, find all solutions in the interval from 0 to 2 pi. Remember, if you see an identity, replace it. So I actually see two possible identities here, but I think the best way to solve this problem is by noticing that this first part has a rotation of 2, and this angle does, and this one only has a rotation of 1. So my suggestion will be replacing sine of 2x as a double angle identity with what it really is equal to, and so let's look at that. Sine of 2x, here in the double angle formulas, is equal to 2 sine x cosine x, or 2 sine theta cosine theta. So I'm going to replace this with its identity. 2 sine x cosine x equals 2 cosine squared x. Now, in my experience, and probably yours, in order to use factoring or anything really useful, we need this equal to 0. So let's move the 2 cosine x over by subtracting it. So we have 2 sine x cosine x minus 2 cosine squared x equals 0. I now notice that we have a greatest common factor in the first and second terms. We can take out a 2, and we can take out a cosine of x. And if we do so and divide this out, we're left with just sine in the first term, and we're left with a single cosine in the second term. If we now set both pieces equal to 0, 2 cosine x equals 0, and sine x minus cosine x equals 0. If we divide by 2 here, we get cosine x equals 0, or you're asking yourself on your unit circle, where do your x values equal 0? So if we look at that, x is 0 at pi over 2 and 3 pi over 2. So there's part of our answer. Now the second piece is a little strange, but think of it this way. If you move the cosine back over, you're asking where, at what angle, do your y values equal your x values? So if we look at the unit circle, the only places that the x's and the y are the same is at pi over 4 and at 5 pi over 4. That's the only place on the whole thing that both x and y are the same value. So my two answers would be pi over 4 and 5 pi over 4.